Here's the 25th.
I have a question.
A question. Let's do it.
This one.
Okay, consider the following. This is an infinite series question.
Yeah.
And n equals 0, infinity, -1 to the n, 2n plus 1 factorial. Consider the following. Oh, approximately, we haven't done that yet. We're doing that today.
Oh, okay, that's right.
We're doing that today.
Why is this?
That's a Taylor series. They're telling you what it is. See, all right, I did tell you that you could use an alternating series to approximate the result. We could do it, well, we could do it today. But the fact that that's equal to the sine of 1, we could do it. Here, let's do it. Here's what I did tell you. Let's take a look at this series. When n is 0, we get 1, -1 to the 0, which is 1, over 1 factorial. When n is 1, we get a -1, we get a minus. Okay, this is an alternating series. And when it's 1, you get 3 factorial, 1/6. Okay, then we get plus. When it's 2, this will be a plus. You get 5 factorial is 1/20th. Minus, etc. As you keep on going, one thing we're going to show today is that that's equal to sine of 1 radian. We're going to do a power series for sine x, and it'll be x here, x cubed, x to the 5th, etc. We're going to do that. That's one of the things we're going to do today. It's an alternating series, and I mentioned the other day that you could take the alternating series and do an approximation for the sum. Clearly, this alternating series converges. Not only does it converges absolutely. It doesn't even have to alternate to converge, because 2n plus 1 factorial increases fast enough to cause the series to converge. So, what they're asking you in this thing is how many terms do you need? So your approximation is, what error they want you to have? What's the error?
Error of less than 0.001.
001?
Yeah.
Okay. So here's what you have to do. If you use one term to approximate sine of 1, your error is 1/6. That's 0.1666 repeating. The error is always the next term. Hey, if you use the first two terms, 1 minus 1/6, your error is going to be 1/20th. So what is 1/20th? 1/120th equal to? So your error in that case for n equals 2 terms would be less than or equal to the next term, 1 over 120. Now what is 1 over 120? It's 0.01666. I don't know, I'm making it up. What is 1 over 120? 0.001666 repeating. Somebody have this? I'm going to guess. Somebody just do 1 over 120.
0.008333.
Oh, that was close. Oh, way on. Okay, put 0.08333 repeating. Now, that's not good enough. We need an error less than 1,000th. We have 8 thousandths here. So n equals 3, our error. The next term, now you got to figure out the next term. This is when n equals 0, 1, 2, 3. For 3, you've got 6, 7 factorial. 7 factorial is 5,040. All right, what's 1 over 5,040?
0.000198. 3 zeros.
3 zeros.
198.
This is good enough, 198. This is less than this. So what you need is to do 3 terms, n equals 3, to get an error that's less than the error they're asking for. Okay, so you need n equals 3, which means you need 4 terms, 3 terms. 0, 1, 2. That's 3 terms. 1, 2, 3. 3 terms would be it. N equals 3.
So what would they be asking for in a question like that?
What are they asking? How many terms?
And smallest number 1 second. Error. They use a graphing unit to approximate the sum
Oh,
of
see,
series.
I'm the graphing kind of thingamajigger here. All right, go ahead. Use a graph, well, that was me. Okay, we did it out, though. Go ahead. So what do they want for an answer? The number of terms?
The first one, they ask, sum of the convergence series with an error of less than 0.001.
We did that.
Okay, the second one is use a graphing utility to approximate the sum of the series with an error of less than 0.001.
We did
Sum
it.
of the series.
Oh, so now they want me to actually add them up. So what they want is to add them up. So I'm saying this, sine of 1 radian is approximately equal to, this is what we're going to do tonight actually, 1 minus 1/6 plus 1/20. If you do this, here, let's do it. Let's figure it out. So you get 120 minus 20 plus 1. That's 101 over 120. Okay? All right, I need someone to do 101 over 120.
0.8416 repeats.
8416 repeating?
The 6 repeats.
Okay, good. Now, that's our approximation. Now we need someone to be in radian mode and do the sine of 1 radian.
0.84147.
0.84147? Thank you. You'll notice that this difference is less than the 001 error that we needed. Our approximation is better than 1/1000th of the true value for the sine of 1. So this is what, I think that this is what they want. They want your approximation here. So I don't know what they want, what form they want it in though.
Yeah, the second one is right, yeah.
Okay, so that's what they want you to do. Here's what we're going to do today. We're going to develop an infinite series for sine x, cosine x, and e to the x. We're going to develop this. And then we're going to do sine x, and we're going to take some of these terms, and we're going to get an error with our infinite series. This is how your calculator actually works. When you do the sine of 1, when he just did the sine of 1, what does your calculator do? It's not a table that's built into the calculator that does the sine of 0.1 or 1 radian for every possible value you could put in. What's built in is circuitry that does the sine of 1 radian as an infinite series. See, what we want to do, one of our goals today, is to get the sine of x as a series, where the series terms are additions, subtractions, multiplications, and divisions. Circuitry can be devised to do these things. You cannot devise circuitry that will do the sine of x, that transcendental function. But you can do circuitry that will do additions, subtractions, multiplications, and divisions. Simple circuits will do that. So you build the simple circuits in that will do not the infinite series, but so many terms of an infinite series. The number of terms is determined by the error that's necessary. We're going to do something today where the error is going to be less than 0.000000000000001. 15-digit accuracy we're going to do with our infinite series approximation. We're going to do it, okay? So anyhow, that's what they're after. But we're going to do that today. But the homework exercise was legitimate because I did mention on an alternating series, your error is less than the next term. So by knowing that, you could do the problem. All right, any other questions? Okay, let's move on. Wow. Here's what we're going to do. We're going to do power series. Okay, we're going to do power series. What the heck is a power series? Yikes. Here's an example of a power series. This is a power series. You'll notice there's a variable in here now. All right? This is equal to a sub naught x to the 0 power, which is 1. This is a sub naught plus a sub 1x plus a sub 2x squared, a sub 3x cubed, etc. Keeps on going on forever. Okay? Hey, Liz, how you doing? Now, here's what we're going to be interested in. Given a certain power series, For which values of x does the power series converge? For example, here's a power series. Actually, this is a power series. This is said to be centered at 0. You can have power series. I should mention this. Centered at some value c. We're going to be concerned about our power series centered at 0. But these power series can be shifted c units left or right. Let me give you an example. Here's a power series. How simple should we start here? Let's do a simple one. Here's a power series. Let's write out a few terms. When n is 0, x to the 0 factorial is 1. When it's 1, we get x over 1. When it's 2, we get x squared over 2 factorial. 3, we get x3 over 3 factorial, etc. That's a power series. Here's the question. For which values of x does this power series converge? Any ideas right off the hat before we actually do it? Listen, what are you doing way over there? I can't even see you over there. That's not, oh man. All right. Any ideas for which x's this power series will converge?
For n of 0 converges at 1.
Say that again now.
N of 0 converges at 1.
Well, the n, okay, what I'm asking you for is give me a value for x that I will put in there for x, and then ask the question, does the series converge? For example, if x is 1, does the series converge if x is 1? 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. Does that series converge?
Does it go fast enough?
What's that?
Is it fast enough?
Do you think so? We got a factorial in the denominator? Is that going to 0 quickly enough to converge? You bet it is, absolutely. How could you prove it? You would prove it with a ratio test. A ratio test would prove that that series does indeed converge. Ugh, maybe we should do it out. Okay, let's just do that one for x equals 1. Let's just test this one. There's the series. Okay, let's prove that it converges with a ratio test. Let's take the limit. N plus first term over the nth term. Okay, ratio test. We did this last time. That's n factorial, n plus 1 factorial. We can simplify that. What does n factorial over n plus 1 factorial simplify to?
1 over n plus 1.
Thank you. And what's that limit as n goes to infinity? 0. Good deal. And that's less than or equal less than 1. As long as that limit is less than 1, the series will converge. Okay? In a ratio test, if that limit's less than 1, the series converges. If it's greater than 1, the series diverges. If that limit's equal to 1, then what happens? What can you say at that point? What is it? The test fails. Atta-way. KB, good deal. Okay, so the test fails. No, it's CB. Is it CB or I never get that straight, Carol. It's CB or KB? KB. It's K. I said it right, but you gave me a weird look, like Burns, you're wrong. All right, but anyhow, I've never seen that look before. All right. Anyhow, 0 is less than 1. Yes. So the series converges. It converges for an x is equal to 1. Does it converge for x equals 2? Listen, trust me, we're not going to do them all like this, but let's just see what we got here. For x equals 2, what about this series? Does it converge for x equals 2? I'm talking about this series now. All right, hold on. I messed this up. Arrgh. All right, hold on, I got it all messed up here. X is equal to 2, I got 2 to the n over n factorial. I'm sorry, 2 to the n over n factorial. I'm letting x equals 2, 2 to the n over n factorial. Does this series converge 2 to the n over n factorial? Yes, who said that? Good deal.
Isn't it contingent just because of the n factorial?
The factorial increases a lot faster than the exponential numerator, therefore it does converge. It converges for 2. Here's what we want to know. We want to do something where we can find out for which values of x the series converges. I don't want to have to test them one at a time. Let's find out for all x's, which x's work. And this is what you do. To test the convergence for a power series, we're going to use a ratio test. And we're going to solve for x. And we're going to find the x's that have the ratio test say that it converges. For which values of x does the ratio test say it converges?
One second. The bottom one, what value does the 2n over n factorial converge? Where does it converge?
It converges, it has some sum. I have no idea what it is. But it does have a sum. It does converge. What is that sum? I don't know. Okay, but it does converge. Okay. I don't know if anybody knows. Oh, he knows.
You know that based on what?
I know that based on the fact that this is a factorial down here, and this is exponential up here. And one of the things I said last time was that the rates of relative increase is a sure way to determine whether these series converge or not. The fact that factorials increase a lot faster than exponential forms means that this series is going to go to 0. That nth term is going to go to 0 quickly enough to cause the series to converge. Okay? And we can prove it with a ratio test. Okay? We proved it for x equals 1. We could prove it for x equals 2. It would come out to be the same thing. All right? It would come out to be exactly the same. It would converge. But now what I want to do is generalize and find out for which values of x does the series converge. Okay? You ready? No, we're not. I can see we're not. We're not ready. Hold on, we're getting there. Oh, you're ready? Oh, you were writing a letter to your PayPal friends. No, that's not right. PayPal. You don't write PayPal. That's not even. Never mind. Forget that. Okay, here we go. So here's the thing. Yes. Thank you. That's what I was trying to come up with. All right. Let's take a look at this power series. Okay. X to the n over n factorial. What we wish to do is find out for which values of x this series converges. We already know that it converges when x is 1 and when x is 2. Let's do it in general. And here's how you do it. You use the ratio test. You take the limit as n goes to infinity, n plus first term over the nth term. And what we want to do is find the x's that cause that limit to be less than 1. That's what the ratio test is. Okay? For those x's that cause this limit to be less than 1, the series converges. That's what we're looking for. Let's do it. You got x to the n plus 1. You got an n factorial. We have an x to the n. We have an n plus 1 factorial. We want to find the x's that cause that limit to be less than 1. We can subtract the exponents. We got an x. N over n plus 1 factorial gives us n plus 1. Now, let's take a look at this. N is going to go to infinity. For which values of x will this limit be less than 1?
So is it x to the n plus factorial?
N plus 1.
Looks like a factorial.
Well, the dot is a multiplication symbol. And it wouldn't make any sense to put.
It didn't,
Yeah,
that's
that's
why
right.
we're asking.
Okay. I'll agree with you on that. Here's my question to you now. For which values of x will this limit be less than 1? as n goes to infinity.
All of them?
Who said that? Atta-way, man. Look at he's obviously out in the sun all day today. He's always sunburned, and he's still thinking at this level. Atta-way. Good job. All right. Yes, all of them. It doesn't matter what x is. As long as n is going to go to infinity, stick any x you want in there. A million, a billion, a trillion, it doesn't matter. For any given value of x, that limit's less than 1 because n is going to go to infinity. All of them, okay? This power series converges for all real numbers. Okay? The x's are from negative infinity to infinity. Okay? This is called the interval of convergence. Okay? There's a radius of convergence. The radius of convergence is the distance from the midpoint of the interval to either endpoint. Okay? Well, the radius of convergence for this interval is infinity. On your test next Monday, Thursday's review, Monday's the test. Yeah. On your test, I will ask you for the radius of convergence for a given power series. Okay? The answer for this particular one would be r equals infinity. This converges for all real numbers x. Okay? Let's do another one.
Is that based on the expression is less than 1?
Yes, it's based on the fact that for any given value of x, this limit is indeed less than 1. And the ratio test is satisfied, okay? The ratio test says if you get a limit less than 1, the series converges, okay? It converges for all real numbers x.
I think you're doing examples, but
Say that again?
to find the radius, you said you go from x to the...
You go from the midpoint. Now, see, you got infinity. That means negative infinity to positive infinity. The midpoint would be 0. From 0 to infinity is infinite. The radius of convergence is infinite. It doesn't make that much sense in this context when you have an infinite interval of convergence, but the next one we're going to have a finite interval of convergence. It makes a little bit more sense. All right, let's do another one. Let's do this power series. Let's do 3 to the n over, how complicated do I want to make this? Do I want to make it real complicated? No, I don't want to make it real complicated, but let's do this one. Times x to the n. This is not too complicated, right? Okay. Let's take a look at this one. Here's a power series. Let's do a few terms. Yes?
So is this it's not over anything?
Over 1. You can put it over 1 if you'd like. The power series, I'm going to leave it just like, put it over 1 if you want. I was thinking about it, but then I figured if we do I'd step back and do an easier one than what I was intending. Because, no offense, but I think I got to start back a little ways here. Because just looking around at you guys. Yeah, okay. All right, so let's do a few terms. N is 0. So I have 3 to the 0, 1, x to the 0. I got 1. Plus 1. I have 3, 1 to the n is 3. Plus 2. I have 2 to the n. I'm sorry, 3 to the n times 2 to the n. That's what, like 6 to the n or something like that? All right, hold on. n is 0, I have 1. n is 1, I've got 3 times 1. n is 2, I've got 9 times x. Oh, man, I'm screwing this up. All right, I am screwing this up.
What is the value of
It's
x?
just 9x.
Yeah, hold on. n is, yeah, we got to find the x that causes it to converge. The x is still should be there. When n is 0, I've got 3 to the 0, 1. X to the 0 is 1, so I have 1. Now n is 1, so I have 3x plus. Okay. Now it's 2. I have 9x squared. Okay. I have 3. I have 27. Okay. X cubed, etc. This is my power series. Boy, I finally got it. All right. All right. How's it look?
Good.
Okay. Here's the question. What values of x will cause the series to converge? Can someone give me a value of x that causes the series to converge?
When x is greater than 1?
If x is greater than 1, I'm going to have the series 1 plus, well, like 2, you want 2. Let's start x.
I meant to say n. n is greater than 1.
It's the x that we're looking for. Okay? There's no n's left here. I'm evaluating for n equals 0, 1, 2, 3. I'm looking for the x's that cause the series to converge. Anybody with any idea here?
You know when x is negative 1?
X is negative 1. Let's try it. X is negative 1. Here's what I have. 1 minus 3 plus 9 minus 27 plus 81 minus 243 plus etc. Does that series converge or diverge? It's going to be a long night, I can see this.
What is it?
What is it? No. It definitely diverges. It diverges. Why?
Does it bounce between extremes?
Well, yeah. Is the nth term going to 0? That's the simplest way to see this. Is the nth term going to go to 0 here? No, it's not. Okay, the nth term is not going to 0. Therefore, it must diverge. Another way to look at this. It's a geometric series. What's r in this geometric series? What's our common ratio here? No. What do we multiply each term by to get the next term?
3.
Negative 3. With r as negative 3, the geometric series will diverge. In order to converge, the absolute value of r must be less than 1. Ooh, you guys up with me on the homework and stuff here? No, I can see not. Who can I look to? I can't look to you, Devin? Oh, then I can't look to anybody. Oh, man.
Wait,
Maybe Brendan. All right, go ahead, Luke.
how did you come to
Louis.
the conclusion it was negative 1?
No, so he gave me somebody gave me negative 1.
Oh, so you just
We just tested it.
you just plug in.
I plugged in negative 1. I said, okay, let's see what happens at negative 1. Does the series converge for x equals negative 1? The answer is no. It does not converge. Look at it. It's an alternating series. The nth term is not going to 0. This series diverges. Also, it's geometric with a common ratio r whose absolute value is greater than 1. It must diverge.
What about
I thought that
1/10?
sometimes alternating series do converge.
Sometimes alternating series do converge. This one does not. We have an alternating series test for
Yeah.
alternating series. This is not one of them, okay? So, yes,
What would 1/10?
1/10. That's interesting. Let's take this. Let's take x as 1/10. Let's see. Well, 1/10, here's my series. So what do we have? When n is 0, we get 3 to the 0, which is 1. We have 1/10 to the 0, which is 1. Plus, x is 1/10. N is 1, so I have 3 times 1/10 plus n is 2. I've got 3 squared, 9 times 1/10 squared is 1/100th. Okay, plus now I'm going to have 27 over 1,000 plus 81 over 10,000 Okay? Here's my series. Does it converge? Here's our series. Let me plug it in here. And I can rewrite it this way. Okay? I could rewrite it this way. Does that series converge?
Yes.
Who said yes? Rabin? You said yes? Good. Why?
Because the denominator is increasing faster than the numerator.
Yes, it is. And that's really sufficient. If you want an exact reason, what kind of series is this? This is geometric. Okay? What's R here in this geometric series?
1/10.
No, not 1/10. 3/10. Okay? Every term is multiplied by 3/10 to get to the next. That's what happened here. That's what this says. And if R is 3/10, the absolute value of R is less than 1, the series will converge. Not only does it converge, we know what the sum is. Okay? We know the sum of this, okay, is equal to A 1 minus R is 10/7. That's the sum of that series, but we're not going to be interested in the actual sum. We are interested in the fact that it does converge. Okay, so right now we have two values. -1, series diverges. 1/10, series converges. What we really want to know is what is the set of all the x's for which the series converges. That's what we really want to know. Okay, let's do it. How do you determine those x values? You use the ratio test for convergence, absolute convergence, and we solve for x. Okay, let's do it. Okay, so here we go. Here's our series. Okay, there's our series. Let's take the limit, n goes to infinity, n plus first term over the nth term. We want to find the x's that cause that to be less than 1. It's for those x's the series will converge by the ratio test. Subtract the exponents. Subtract the exponents. Ooh, all the n's are gone. Here's the deal. What's the limit of the absolute value of 3x as n goes to infinity? What's the limit of 3x, its absolute value, as n goes to infinity? Since there's no n's here, what is this equal to? Yeah, it's equal to 3x. As long as there's no n's there, it's just 3x. Let's solve for x. The absolute value of x is less than 1/3. Just divide by 3. The absolute value of a product is the product of the absolute values. If the absolute value of x is less than 1/3, let's take the absolute value out of there. We can write this without the absolute value. You guys can do that, right? If you take the absolute value out, that says that x is less than 1/3, but greater than -1/3. It's for those values of x, the series will converge. This is the interval of convergence. Except for one thing. The one thing is this. What happens at 1/3? What does the ratio test tell us for x equals 1/3? It's inconclusive. The test fails at 1/3 and at -1/3. It fails at those endpoints. And what you've got to do for the interval of convergence is to test those endpoints to see if they work or not. Sometimes they will work and sometimes they won't. It's easy enough to test this one. If x is equal to 1/3, does that series converge? We end up with the sum of 3 to the n times 1/3 to the n. The 3 to the n's cancel. We get the infinite sum of 1s because the 3 to the n over 3 to the n cancel. Does an infinite sum of 1s converge? No. Keep on adding 1 up infinitely, you get to infinity. Does it converge for negative 1/3 at the other extreme? You got a negative 1 to the n. Does that series converge? Negative 1 to the n.
Yes.
No.
I thought they just cancel each other out.
Yeah, no, it doesn't. The limit's not 0, so they don't. What happens here, that's a controversial series from way back. If you group them right, the sum will be 1. If you group them the other way, the sum is 0. There is no sum. Okay? And if you go to numberphile.com, they do a whole talk on that series, and they end up proving that series is equal to like 1/12 or something like that. But it's all based on a false premise. So neither endpoint causes the series to converge. This is indeed the interval of convergence. What's the radius of convergence for this power series?
1/3.
Yes, it is. Radius of convergence. You guys see that over there? R equals 1/3. It makes more sense now. If going from negative 1/3 to 1/3, 0's in the middle, the radius of convergence is 1/3. Oh, man, I'm working like a dog. Does this make any sense here? Starting to. Good. So far, we've done 2 power series. The first one had an interval of convergence that was infinite, converged for all real numbers. This interval of convergence, negative 1/3 to 1/3, radius of convergence of 1/3. There's one more case. There are 3 cases in all. And guess what on the test? I'm going to give you 3 power series, okay? And there are 3 possibilities. I mentioned for alternating series, there are 3 possibilities, right? Absolute convergence, conditional convergence, and divergence. And I'm going to give you 3 alternating series. There are 3 possible interval of convergences, okay? One is infinite. The second one is some finite number, like 1/3, like we just did, okay? The third one we're going to do right now, all right? Here we go. Let's try this one. All right, we're getting there. We are getting there now. How about this one? Okay, let's do this. How about this? Okay. Let's take a look at this one. Okay, let's take a look at this one. That's good. I have a little musical introduction. Let's take a look at this series. Da, 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 da. Here it is. All right, let's do a couple terms. N is 0. Get 0 factorial x to the 0. That's 1 plus 1 factorial is 1x plus 2. We get 2 factorial, 2x squared. 3, you get 3 factorial, 6x cubed. 4, 24, x to the 4th, etc. That's our series. Question is, for which values of x will the series converge? Here's what I need for one super bright student. I need one value of x that causes this series to converge. And guess what? There's only one value of x that causes the series to converge.
0?
Yes. At x equals 0 only. Nice, Dylan. X equals 0 is the only x for which this series converges. This interval of convergence is the single point x equals 0. The radius of convergence is 0. Let's prove it. Let's use a ratio test. Let's see why. Let's take the limit, n goes to infinity, of the sum. I don't want the sum. Holy mackerel. All right, the limit as n goes to infinity. I want the n plus first term over the nth term. And I want to find the x's that cause that limit to be less than 1. Okay? Find the limit as n goes to infinity. Let's see, we get n plus 1 here, and we get an x. Now, what's this limit for any given value of x? Is there a value of x for which this limit is less than 1, in other words? N's going to go to infinity here. At 0 only. That's the only value of x that causes this to be less than 1. Any other value of x, this thing will go to infinity and be less than. So at x equals 0 only is the only value of x. So what do we have? Interval of convergence. Is x equals 0, the single point. Radius of convergence is 0. Those are the three possibilities for a power series. Infinite interval of convergence where all real numbers cause it to converge. A finite one where there's a certain interval for which the series converges. They may or may not converge at the endpoints, so you have to test them out. And then a 0 interval of convergence, a 0 radius of convergence. It converges only at x equals 0. Okay, how we doing? Okay, here's what we're going to do now. We're going to design a power series on our own. Okay? We're going to design one. Here's what we want to do. I want to come up with a power series that's going to be able to at least approximate some transcendental function, some function of x, like sin x, or e to the x, or cosine x. Okay? I want to come up with a power series representation of this transcendental function. And I want it to meet certain criteria. So here's what I want. I want to come up with a power series. Here, let's do it in terms of n first. Nth degree. Let's start off with an nth degree. It's called a Taylor polynomial. Okay. Nth degree Taylor polynomial will look like this. It'll start off at the first term, a sub naught, plus a sub 1 x to the first, and a sub 2 x squared, and a sub 3 x cubed, etc. It's a power series. Okay? It's a power series. Here's what I want. Let's say we're given some function f of x. Okay. Here's what I want to have happen. I want our Taylor series, our power series, this polynomial, to agree with our function at 0. So at x equals 0, I want p of 0. Now, what's p of 0? What's this power series, this polynomial equal to when x is 0?
0.
No. What is it?
A0.
Yes, a sub naught. Good job. Okay. A sub 0. Okay. I want at x equals 0 our power series a sub 0 to equal the function at 0. I want them to be equal at 0. I'm going to start there. Well, this tells me that a sub naught is f of 0. So here's what I have right now. My power series is f of 0 plus a sub 1 x plus a sub 2 x squared, a sub 3 x cubed, etc. What I've done, I solve for the first constant, f of 0. That way, my power series and my function agree at 0. Okay? Well, what else should I want? Here's what else I want. I want my power series first derivative at 0 to equal my function's first derivative at 0. I want those two to be equal. This is going to take a while, so hang in there, all right? You ready? We're going to develop this thing. The derivative. Now, what's the derivative of my power series? What's the derivative of f of 0? Where f of 0 is some constant. It's 0. Forget it. What's the derivative of a sub 1 x? What is it? A sub 1. What's the derivative of a sub 2 x squared? What is it? 2a sub 2x. Take the derivative. Plus, what's the derivative of the a sub 3x cubed? 3a sub 3x squared. And it keeps on going. Okay. What's the derivative at 0? All the rest of the terms are zeros. It's a sub 1. I want my power series, my polynomial's derivative at 0, a sub 1, to be equal to the function's first derivative at 0. I want those two to be equal. That tells me that a sub 1 is the derivative, first derivative of our function at 0. So here's what I have right now. My power series, my Taylor's polynomial, is equal to f of 0 plus f prime of 0 x, this is a sub 1 right here, plus, okay, I got this, plus a sub 2 x squared plus a sub 3 x cubed, etc. This is what I have right now. Okay? Okay, yes?
Where did that f prime 0x come from?
This comes from, because we solve for a sub 1 to be f prime of 0. Okay? So for a sub 1, put an f prime of 0.
Okay.
And that's what I have. Okay? Okay. All right, what else do I want to have happen? Here's what else I want. I want my approximation, my polynomial, my Taylor series polynomial, my power series, to agree with the function's second derivative at 0 as well. Okay? I want that to happen. So, here we go. The second derivative. Okay, of my function is equal to, here's the first derivative, let's take the second derivative. The derivative of a sub 1, that's a constant, forget it. So I get 2a sub 2. I'm taking the derivative of this now. Plus, okay, I need someone to tell me the derivative of that term right there. It's 3 times 2. I'm going to write it as 3 times 2. It is 6, but I'm going to write it as 3 times 2. Because we're going to get a pattern here. Now, I haven't written the next one out. What would the next one be? Even though I haven't written it out yet, but you can figure it out, I think. What would this one be?
4 times 3.
Yes, a sub 4x squared. Very nice. Etc. Okay? Okay, everybody with me on that? Okay. The second derivative at 0 is going to be 2a sub 2, and all the other terms are 0 when x is 0. And what's that equal to? My second derivative of my function at 0. I want those to be equal. This tells me what? A sub 2 is equal to f double prime of 0 over 2. Solve for a sub 2. Okay? So here's what I have right now. My polynomial is equal to f of 0 plus f prime of 0 x plus a sub 2 now is f double prime of 0 x squared over 2 plus a sub 3 x cubed plus etc. All right, we're not going to do this too much longer. Okay, we need to get a pattern going here. All right, I think I need to do one more term and then we're going to get a pattern. Okay, you ready? Okay, go ahead, Edwin. No, you okay?
I was gonna guess
You can ask.
Would third term be f to the third derivative 0 over 6?
Yes, it is. Yes, it is. John. I'm going to do that one out, and then I'm going to ask the rest of the class. Obviously, Ed, when you're up here, I'll have to bring everybody up to your level if that's possible. All right? We're going to check it out. Okay, ready? Whoa! Yes, I could. Okay. Rabin, how you doing? What are you doing?
No, everything.
Oh, you're looking for your break? Oh, yeah.
As
Before class, they had a bunch of people saying, Burns, you're working us to death here, and sometime we need a 5 or so minute break. And I stupidly agreed to this concept, okay? Well, I want to develop this first, and then we'll have a break, okay? We'll do that. So, we're going to do jumping jacks or something during the break or something? We could do that.
To the left on the, around the green.
Around the green, yeah, good deal. Coffee, yeah, all right. Well, you guys can. We'll take a 5-minute break in a few minutes, but I'm going to go one more turn. I'm going to develop the general form here. So here we go. Okay. Right now, our polynomial, our function, agrees with our function, our transcendental function, at 0. They have the same value at 0. They have the same first derivative at 0. They have the same second derivative at 0. What else do I want? I want the third derivative at 0 to be the same. So let's do it. Let's find the third derivative. The third derivative of our polynomial, okay, is equal to, okay, here we go. Here's our second derivative. Our second derivative is this right here. I'm going to take its derivative. So what I'm going to have is the derivative of the 2a sub 2 is 0. That's a constant. The derivative of 3 times 2, a sub 3x, is 3 times 2, a sub 3. Plus, the derivative of the next term is 4 times 3 times 2, a sub 4x. Now, I haven't done the next one, but I need someone to tell me what the next one would be.
5 times 3 times,
Right.
times 4 times 3 times 4.
It's 5 times 4 times 3, a sub 5x squared. Okay? That's what it would be. Okay? What's the third derivative at 0? Jeez, that's a 3 there. At 0, all these terms would be 0. It's 3 times 2, a sub 3. And I want that to be equal to my function's third derivative at 0. I want those two to agree. Thus, a sub 3 is equal to the third derivative of my function at 0 over 3 times 2. Okay. Which is what Edwin said a little while ago. Let's make the leap. Let's take the jump right now. My polynomial is going to equal f of 0 plus f prime of 0x plus f double prime of 0 over 2x squared plus f triple prime of 0 over 6, 3 times 2, x cubed plus, and someone gives me an expression for the nth term. Call this the 0 term, 1 term, 2 term, third term, okay? Call this the 0th term. What would the nth term be? This is 0, 1, 2, 3. F, what derivative?
The n power
Yeah.
derivative of f over n factorial?
You bet it is. That's an nth degree Taylor polynomial centered at 0. Okay? What we're going to do is let n go to infinity. Okay? Okay? This is called a Maclaurin series. Maclaurin was Taylor's student. Yes?
How come like throw with the ace and 5 and then 5, 4, 3, 2?
5, 4, 3. Yeah, when I take the next derivative, the 2 will come out. See, I stopped here, but when I take the fourth derivative, okay, yeah, the 2 will come out, and I'll get 5 times 4 times 3 times 2. Yeah. This is a Maclaurin series. When it's centered at 0, it's called a Maclaurin series. Brooke Taylor was the mathematician. Maclaurin was his student. It is said that Maclaurin did all the work, and Taylor, the teacher, took all the credit. So if you guys do discover anything, just let you know that's how it works, okay?
You can bring it like by your office?
Yes, just drop it by. If you discover, like, what's the $1 million one? The $1 million one, if you can prove the Riemann hypothesis. If you do prove it, just drop it off. Yeah, that's.
And then the largest prime number?
There is no largest prime number, but the largest known prime number is worth about $1 million. Yeah, if you can discover the next largest known prime, yeah, that's probably exactly right. There's a whole bunch of them out there that are unknown at this time, and if you can prove one of them, you'll be rich and famous. Okay.
Well, would you just have to have an array of computers just continue?
Yeah, well, okay. Well, they have arrays of computers working on some of these problems right now. You'd have to come up with something better somehow. Actually, if you simply solve the traveling salesman problem, you would be rich and famous. And it's a simple matter of starting from one capital of one of the states. Say you start from Boston, and you have to travel to all the capitals of the 48 contiguous states and end up back at Boston. If you can prove that you have the shortest possible route, you will be rich and famous. That is called an NP incomplete problem. To solve it is unbelievably complicated. You basically have like 48 factorial possible solutions, and we're talking about trillions and trillions of solutions. And there's no known way of doing it. There are algorithms and strategies. There's greedy algorithms and short distance algorithms and all bunches of ways to do it, but no one has proven that they have the shortest possible route. Anyhow, there's a lot of math problems out there still left to be proved. Okay, here's what we want. This is an nth degree. As soon as you stop, you've got an approximation. You have equality, okay, for our function. So our function f of x is equal to the sum, okay, of all these. And that would be the nth derivative at 0, x to the n over n factorial. Okay? This is a power series. This is our Maclaurin series. This is our Taylor series centered at 0. It's actually equal to our function as long as we go to infinity. As soon as we stop, we have an approximation. We're going to use this to develop infinite series for sine x, cosine x, and e to the x. And then we're going to see how accurate our approximations are. And then we're going to do a couple other things. All right, if you guys want to take a 5-minute break, that's fine with me. Go ahead. Take a 5-minute break. Do whatever.
Just leave me here. I don't care.
Leave me here all alone. I don't care. That's all right. I can handle it. 7:06. I'm going to start back up.
Are you going to leave the recording?
Where's Devin? What should I do?
Just leave it recording.
Okay. Yes.
What do we use this for?
Your calculators use it to calculate sine of anything. Cosine, e to the x. It's actually used every day. You probably use this more than you use anything else. As soon as you put in the sine of 1 radian in your calculator, I'll show you. It does a Taylor series approximation for so many terms to give a given degree of accuracy. So it's used a lot. We'll do it.
What else do we have to cover today?
Well, we're going to also use this to prove one of the greatest formulas in mathematics. Euler. What's that?
E to the I pi?
Yes, we're going to do that too. E to the I pi is -1. So we've got a couple things left to go. It's not that much.
So we have review Thursday and then test Monday,
That's it.
and then we're done.
Then we have a review for the final, and in that review for the final, I'm going to give you a sample final, where if you pass that, you can be done. And then the actual final, the second final is the Monday.
So next Thursday is on review.
Next Thursday, a week from this Thursday, is a review for the final, yes. And you can be done that day. That Thursday is May 5th, right? Yes, that's Cinco de Mayo. Yes. It's unfortunately my birthday.
So
Cinco de Mayo?
So yeah.
you should just pass.
So I may not be here. I may have someone come in just to give you the test and stuff. No, I'll be here. What's that, Abby?
Well, I was gonna talk to you about it after class, but I mean, we're on break, so I may as well.
Oh, go ahead.
So on Monday, I
Monday.
have a meet that I have to go to.
Sure.
So I don't think I'll be able to take the test on Monday. Is there any way I can do it?
Yeah, anytime.
Okay.
You tell me what's up. What happened? What works for you?
Well, if you want me to take it before,
I don't care.
well then I can take it either. I can take it Tuesday.
Fine. Tuesday. Oh wait, Tuesday when? Morning? No. See, I'm not here
Oh,
Tuesday
okay.
night. It's like the only night I'm not here. I'm here Monday night, Wednesday night,
Can I
Thursday
take
night.
it Wednesday night?
Yeah, Wednesday night's fine.
Oh, great, thank you so much.
No problem. Wednesday night, yes, I'll be here. As a matter of fact, Wednesday night, I'll be giving my Algebra 1s a final. You could even sit in with those guys. Was that worth it? Was it? Just to walk around and get out of here? All right, fine. You got water? Okay, that makes sense. You got some good stuff. You guys got some. What do you got? What is that? Like Red Bull or something? Energy Amp. Wow. Woo!
But then I can.
Carolina, you need some Energy Amp. You gotta try some. Wait, did you have your whole computer done purple and for prints?
Yeah.
Oh, you did? Oh, that's where it was? It came? Oh.
No, you buy it separate.
Yeah, I figured you bought it for prints and his aren't.
Oh.
No, huh? Oh.
We still have one more lab, dude.
Yes, we do have one more left.
Do next week.
Yeah. I'll explain it Thursday when I do lab and redo. You guys didn't even know Prince? I mean, he's kind of before your time.
I know Prince.
What? No.
Prince.
Oh, you do?
Not no Prince.
Well, I because when I give you guys like like the Shirelles and stuff, you guys don't know Shirelles. No, well, they're not as big as Prince, I guess. But he's more 80s, right? Well, he did 90s.
He's still
Michael
big.
Jackson was 80s too.
He has a
But you know Michael
Like
Jackson.
Prince was still touring.
Right.
Like
yeah, and he has
Oh, was
hundreds
he?
of songs that
Yeah.
are still unreleased.
Oh, all right. Okay, fine. Okay. I was never a big Prince guy.
I'm not.
It was, yeah. you know, Party Like 1999, that was a cool song, but I don't have it on my iPad or anything.
I think they're still trying to figure it out.
Figure what out?
Is death Purple Rain?
Purple Rain, I know, yeah, the movie Purple Rain, I didn't think it was such a hot movie. I vaguely remember it. The song was okay. Oh, yeah, where is he? Oh, I'm sorry, Chris, I'm insulting. All right. He's deaf? I'd be willing to bet it was some form of drug related. I mean, I don't know for sure. I'd be willing to bet though. Okay. Oh, we're ready. I knew this was happening. Look at that. We gotta get going. All right, we gotta go. Let's do it. All right, so here's what we're gonna do. This is a power series, okay? What we want to do is use this power series to develop an approximation for three particular functions: sine x, cosine x, and e to the x, okay? Let's do sine x first. So here's our function. Our function is sine x. Okay. And what this says to do is find f of 0. Well, let's do that first. What's f of 0?
0.
0. Thank you. We need f prime of 0. Well, to do f prime of 0, we should do f prime of x. Sine x, the derivative is cosine x. F prime of 0, cosine of 0 is 1. Okay. We should do f double prime of x. The second derivative would be a negative sine x. The second derivative at 0 is 0. Okay. Third derivative. Third derivative at x. The derivative of negative sine x would be a negative cosine x. The third derivative at 0 would be negative 1. Okay? Check it out. What I'm doing is taking these derivatives so that I can put them in here and do my Taylor series for sine x. Now, the fourth derivative for x, what's the derivative of a negative cosine? Positive sine. Right, back to sine again. All right, so this is pretty cool. The fourth derivative at 0 is going to be back to 0. Okay? And now the fifth derivative would be exactly like the first derivative. It'd be cosine, and the fifth derivative at 0 would be 1. So repeat this. Here, let me write that out. Fifth derivative at x is cosine. The fifth derivative at 0 is going to be a 1. Okay, this is 1. Okay. All right, so let's write it out. So here's what we have. Okay, you ready? Sine x is equal to f of 0, which is 0, plus f prime of 0, which is 1x, okay, plus f double prime of 0 over 2, but still 0. Then it's going to go minus the third derivative at 0, okay, which is a negative 1, x cubed over 3 factorial. Okay. What I'm doing is substituting in our values that we just found in for those coefficients. Okay? That's what we're doing. Now, plus, what will the next one be?
0.
0. And the next one? positive x to the
Fifth.
5th over
5 factorial.
5 factorial. Nice. And the next one,
0.
0. Then the next one,
X to the 7th.
it will be plus or minus.
Minus.
Minus x to the 7th over 7 factorial plus etc. So here's what we have. Sine x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7th over 7 factorial, etc. This is a power series. Okay? This is a power series. There's a couple things we should do with this power series. The first thing we should do is find the values of x for which it converges. Okay? Because it's for those values of x we can use this to find sine of x. So we have to find the x's for which it converges, so it has a sum. Then what we should do is use a few of these terms to do an approximation for sine. And then what we should do is determine the error in our approximation. Okay? So you ready for all this? Here we go. First thing to do is see what we have for a radius or interval of convergence for this power series. Let me write it this way first. Now you'll notice all these terms are odd terms. Okay, 2n plus 1 will generate those odd terms. The denominators are 2n plus 1 factorial. Okay? And if you take n equals 0, we're going to get a 0 here. That's a 1. We'll get x to the first. We'll get 1 factorial. When n is equal to 1, we're going to get a negative 1. We're going to get an x cubed. And we're going to get a 3 factorial. When it's 2, we're going to get a positive 1, x to the 5th, and 5 factorial. So this is the way to write this compactly. This is our power series. We want to find out what values of x cause this to converge. Because it's for those values of x, we can use this to compute the values of sine. Okay? So let's do it. How do you figure that out? Use a ratio test. Take the limit as n goes to infinity. N plus first term. Over the nth term, and replacing the n with n plus 1. Bless you. Now the nth term. And I'm going to find the x's that cause that to be less than 1. Whoa, that's nasty looking. Wow. Okay. You guys still alive? Okay. Mohit, you okay? I'm worried about you, though. You can see that, all right, huh? Okay. Okay. N goes to infinity. Now, first of all, because we're using absolute value, this is a ratio test for absolute convergence, is what it is. We can forget about the negative ones. We're really testing the positive series here. Throw the negative ones out. The absolute value makes them all positive anyways. We have x to the 2n plus 2 plus 1. We have x to the 2n plus 3 times 2n plus 1 factorial. This guy comes up here. Over x to the 2n plus 1, this one, times. This one here comes down below. It's 2n plus 3 factorial. And we want to find the x's that cause that to be less than 1. Let's simplify. Take the limit as n goes to infinity. Absolute value. 2n plus 3, 2n plus 1, subtract the exponents. We get an x squared. Now, what does that simplify to? We got 2n plus 1 factorial over 2n plus 3 factorial. What does that simplify to?
The 2 factorial?
No. 2n plus what?
2.
That's one of them. There's two terms left. One of them is 2n plus 2. The other term that's left is 2n plus 3, yeah. What is 2n plus 3 factorial? It's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And the 2n plus 1 factorials cancel. Question is, for which values of x will that limit be less than 1? Every value. Boy, Brendan's pretty good. All right? Every value of x for all reals, okay? Converges for all reals. What's the interval of convergence? Negative infinity to infinity. Give me any value of x. I don't care what it is. Square it. So what? You get some finite number. These n's are going to go to infinity. All right? That limit is 0 for any value of x. Okay? In other words, what we have here is a power series that converges for all real numbers. In other words, I can use this power series for any value of x for sine. In particular, we can do an approximation for sine. Okay? Now, let's not do that one yet. I want to do cosine, and I want to do e to the x as well. There's 3 of them that we want to do. Now, we're going to do cosine next. We have sine. Here's what we could do. We could repeat the process we just went through. Find f of 0. Find f prime of 0. Find f double prime of 0 over 2, f triple prime of 0 over 6, etc. And redo it. We could do that. But if we're smart, there's a better way. How can we go from sine to cosine? Yes! We could take the derivative. If we take the derivative of sine, we're going to get cosine, and we could take the derivative of all these terms. And that's exactly what we're going to do. Wow!
Wow. Just trying to read some down.
That's exactly what we're going to do. I got notes all over the place here. Look at. All right, make sure I get these notes reassembled in case somebody needs them. Who am I missing? Anybody important?
Few people are.
Carolina's here though, so who cares? All right. Okay, so here we go. Cosine. Oh, and by the way, what kind of function? Here's sine. I'm going to rewrite it. I'll rewrite it. I'll just do it this way. Here's sine x. What kind of things? What kind of function is sine x, do you think?
Trig.
What is it?
Trig.
Trig. Can't argue with it. It's not what I'm after. What is it? It's not even. Well, look at the exponents here. What kind of function is sine? Odd function. It's an odd function. And check it out. All the exponents are odd. This is an odd function. What kind of symmetry do odd functions have, by the way? What's that? No. That's inverse functions. What's that?
It's oscillating at those 5 of them.
Well, odd functions don't have to oscillate, but they do have one kind of symmetry. What is it? No. No.
Respect to the y-axis.
Who said it? I heard it. Somebody thought it at least.
The origin?
The origin said Devin. Yes, the origin. Odd functions have symmetry with respect to the origin. Another odd function would be y equals x cubed. And if you think about y equals x cubed, it looks like this. Take a point on the graph, draw a line through the origin, continue till you hit the graph. The origin bisects all those lines. Odd functions have symmetry with respect to the origin. Sine has symmetry with respect to the origin. Sine is an odd function. You can see it here. okay, with all odd exponents. Cosine, being the derivative of sine, we can generate its Taylor series by taking the derivative. 3 comes out, cancels out one of these 3's. You get x2 over 2 factorial. 5 comes out, cancels the 5. You get x to the 4th over 4 factorial. 7 comes out, okay, cancels the 7. You get x to the 6th over 6 factorial. There's cosine. What kind of function is cosine? Even. There it is. They're all even exponents. Even the 1 is x to the 0 power. One more we got to do. Let's do e to the x. Now, we can't do e to the x like this, though. Okay, so let's do e to the x. What's the f of 0? If our function now is e to the x, what's f of 0?
Natural log of 1.
Natural log of 1 would be 0. No, that wouldn't be it. It is 1. E to the 0 is 1. What's the first derivative of our function? Yes, and what's the first derivative at 0? Okay, it's 1. What's the second derivative of our function? And what's the second derivative at 0? And again, they're all 1s. So here's what we have. E to the x is equal to 1 plus, they're all 1s. Every one of them is a 1. So the coefficients are 1 plus x squared over 2 factorial plus x cubed over 3 factorial, because here's our polynomial. Okay. All these are equal to 1. Every one of these is equal to a 1. Okay? Okay. X to the 4th over 4 factorial, etc. Okay? What's the radius, or what's the interval of convergence for this power series? For which values of x will this series converge? What is it?
1.
It will, well, it's going to be more than that. What's the interval of convergence here? We could do a ratio test for it. Let's do the ratio test. Let's test it out. Okay. So here's what we have. Okay. We have x to the n over n factorial. I think I did this one. This isn't the first one I did. Did I do this one? Yeah. Oh, I did n factorial times it. Then I did. Yeah. What the? That's the first one I did. Okay. Check it out. What's the interval convergence for that? X to the n over n factorial? It's infinite. We did it out, okay? Because I have foresight. But I don't have this in order. I have foresight, but I don't have this in order. Oh boy, this is a zoo. I don't know. Devin, where? I don't know. The notes are. Okay. This converges for x negative infinity to positive infinity, okay? Infinite radius of convergence. Okay, there's two things we want to do here. One thing we want to do, let me change that. There's two things I want to do here. One thing I want to do is use one of these series to approximate cosine of something. We're going to do what your calculator does. Let's do an approximation for cosine of 0.1 radians. Okay? Here's what we're going to do. Let's do cosine of 0.1 radians. Now I'm going to need a calculator person. Carlos, you good with that thing? Yes? What's that? You can do it, right? Okay, here we go, because I'm going to need somebody that's really good with it. So here we have, let's do cosine. Okay. I'm going to approximate cosine by taking the first 4 non-zero terms, okay? Cosine, 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. I want to go one more. I want to do x to the 8th over 8 factorial, okay? let's take those first 5 non-zero terms. I want to do the cosine of 0.1 radians. Now, if he were to give his calculator this problem of cosine of 0.1 radians, the calculator is actually, it has circuitry that will calculate this little part of the series, these terms, because there's circuits that you can make that will add, subtract, multiply, and divide numbers, okay? It's pretty simple. So, what do we got? 1 minus 0.1 squared over 2 plus 0.1 to the 4th over 4 factorial, 24, minus 0.1 to the 6th over 6 factorial is 720, plus 0.1 to the 8th over 8 factorial, which is 50, 40 times 8. Okay, hold on. It's 40,320, I think.
Factorial?
Is that it? 8 factorial?
Yeah.
It is. Okay. I need Carlos to calculate this as our approximation. Can you do that? Is your calculator that good? Maybe I'm going too far here. I sometimes do that.
I have to test myself, so I can try.
What's that?
I just did it.
You did it? You did it in your head? See, he did it in his head. All right, what'd you get?
I got 0.99500.
Oh, I need way more digits than that.
416.
All right, hold on. Okay, hold on. So you did this thing out. You did our calculation out here. Okay, good. Okay, 0.99500, yes.
41653.
41653. 3?
Yeah.
Any more? You got more digits?
That's all.
Carlos, you got more digits?
No, that's all.
I
What?
can get you more digits.
Give me more digits.
I'm writing it in. 1 second. Sorry. I was checking the factorial before. And
Any more digits?
the 4th. The 24.
We need more digits.
If this doesn't work, I'll stick in Wolfram.
Like, what are you doing? How are you doing it in what? If you got Mathematica, the thing to do is do it in Mathematica.
But Mathematica takes a little while to get on here. Okay, I got 0.995004165,278.
278. Okay, that's better. 278. Okay, that's by calculating our approximation. Now, here's what I need you to do. I need you to be in radians and do on your calculator the cosine of 0.1 radians.
Same thing.
995004165,278. We're exact out to tens, hundreds, thousands, 10,000, 100,000, millions, 10 millions, 100 million, billions, 10 billions, 100 billions, to trillions at least, okay? How accurate are we? We can tell how accurate we are by doing the error. What's the error? The error in our approximation by using these 5 terms to approximate the cosine of 0.1, that error is less than or equal to the next term, which would be 0.1 to the 10th over 10 factorial. That's what our error is. So I need someone to do 0.1 to the 10th over 10 factorial if you can.
To the negative 17.
What is it?
The power is to the negative.
Yo, give me the digits. Give me what you got.
2.8 to the negative 17.
Our error is less than 2.8 times 10 to the negative 17th. In other words, we've got accuracy.
Rounded it to 0.
Yeah, that's pretty cool because 0 error would be kind of neat. But as soon as we stop, okay, we've got at least 16-digit accuracy just by using 5 terms of that infinite series. Okay, just using the first 5 terms. That's how accurate that approximation is. I mean, it is right on. Now, suppose your calculator had to do, instead of 0.1, it had to do 5.1 radians. Would it be as accurate as quickly? No. when you get away from 0, the accuracy is going to decrease considerably. We centered everything at 0. If you're going to go up to 5.1, you should center it at 5. You should shift it over and center it at 5. As a matter of fact, if you had to calculate a radius of convergence, let's go back to a power series. Let's suppose we had something like this. Over, let's say 3 to the n. Let's take a look at this. Because I don't know if you have this for homework, but just in case you do, this is a power series centered at 5. Okay? So if you had to figure out an interval or radius of convergence, the thing to do is not do this series, but shift it 5 units over and do this series instead. Okay? These two series will have the same radius of convergence. After all, it's just a shift. Okay? 3 units over. Can anybody tell me what the radius of convergence is for this series? Just by looking at this and figuring out, because it's going to be geometric and x has to be between what and what?
0.3?
What?
0.3?
Not 0.3, no.
1/3.
1/3. No. Shoot. If that were 3 to the n upstairs in the numerator like I gave you before, it would be 1/3. But it's 3 to the n in the denominator now. So x has to be between what and what?
3.
Yes. Yeah. Boy. Wow. Wow. Edwin, wow. Okay. Yeah, x would have to be between -3 and 3. Okay? That would be, and what about at the endpoints? Does it converge when x is 3? 3 to the n over 3 to the n. Does that series converge 3 to the n over 3 to the n? Does it converge?
No.
It doesn't, because it's 1. It's sum of an infinite number of 1s. Does it converge at -3? -3 to the n over 3 to the n? No, you got a -1 to the n. You got that -1 to the n kind of, yeah, exactly. Okay, this is the interval of convergence for this series. What would the interval of convergence be for this series?
-8 and -3.
It'd be centered at 5. You'd shift it over 5. It'd be 3 units up and 3 units down. It would be from
2 to 8.
2 to, yeah, 2 to 8. That's all the difference would be. So instead of doing an analysis of this, what you should do is this one. You just do the shift. I don't know if you have homework. I wouldn't do that to you on the test, but you may have something like that on the homework where they do shift it. Okay, I just want to point that out. Okay, let's get back to cosine.
When you have x, because it has to be, it can't equal, because when you have -3, your first two terms equal 0.
If you have -3 here, you have a -3 to the n when n is 0, so that's going to be a 1.
And then the next term is -1.
And then it's -1, and then it's going to be +1, and then it's going to be -1 and +1. This series diverges, okay, because the nth term is not going to 0. In any series that you have, if the nth term doesn't go to 0, it's going to diverge. That's the nth term divergence test. Okay, so we have a 16-digit accuracy on our approximation for cosine. And the reason we have that kind of accuracy is because it's an alternating series. The sines and cosines are alternating series. On your test, I will give you the sine or cosine approximation to do. I'll have you take the first couple of non-zero terms and use that to approximate sine or cosine of something or other. And I will ask you for the error, okay? I'll only ask you to do it for like a couple of terms, so you don't even need a calculator for it. But I will ask you that, okay? Just so you know. All right, there's one more thing we got to do. Wow, we're rolling here. Okay. Oh, my notes are all whacked out, though. Okay. The last thing we have to do is this. Let's take a look at e to the x again. E to the x, we said, was 1 plus. Remember, we had all the 1s here. We did e to the x back away somewhere. okay? We had all coefficients that are 1, so we had the x, we had x squared over 2 factorial, x cubed over 3 factorial. We did do this. I'm going to tell you, too, that we can't get the same accuracy in our approximations because it's not alternating. There is a way of finding out what the error is, but it's a little bit more complicated than it is for an alternating series. For an alternating series, you just have to get to the next term. It's a little bit more complicated. Okay, so here's what I want to do. We're going to go into the complex numbers here. Okay, it's the only time this whole course we go into the complex numbers. And what I want you to realize is that I is the square root of -1. I squared is -1. I cubed is I squared times I is a negative I. Okay, it's I squared times I. And I to the 4th is equal to 1. So I to the 5th is back to I again. Okay? And you may say, well, complex numbers, what the heck? What kind of applications do you ever get with complex numbers? Well, I'm going to tell you, when you take differential equations, if you do take differential equations as an engineer, there are certain differential equations that you solve where the solutions are complex numbers. Simple circuits, okay, simple circuits, all right, have solutions where you have to get into the complex numbers and go back out to the reals again, all right? Marconi was developing radio. Did I tell you guys this about complex numbers? Yeah, and in order to solve these systems of equations that he had, these differential equations, he had to go into the complex numbers, solve them there, and come back to the reals again. Okay, they're something you have to deal with. Okay, all right, we're going to deal with it only in this context here. Okay, here's what I want to do. I want to get e to the I pi. I'm going to replace x with I pi. And think about what we have here. We have e, a transcendental number, 2.718281828459045, et cetera, infinite non-repeating decimal. Transcendental, meaning what? It's not a solution to any polynomial equal to 0, okay? I, square root of -1. We have pi, another transcendental number, ratio of a circumference of a circle to its diameter, okay? Unbelievable. Let's substitute for x I pi. So we get 1 plus I pi plus I pi squared over 2 factorial plus I pi cubed over 3 factorial plus I pi to the 4th over 4 factorial, I pi to the 5th over 5 factorial, I pi to the 6th over 6 factorial. So,
Did you take a look at it?
okay. So, what do we have? We have a big zoo. Okay. Okay. E to the I pi. Okay, it's not what I wanted yet. I'm too soon. I was too quick. I want e to the ix first. I'm sorry. This is coming later. I need e to the ix. I need to replace x with ix first. All right? So replace x with ix. It's 1 plus ix squared over 2 factorial. I'm sorry. I was too quick for the substituting for pi for x. Ix cubed over 3 factorial. Ix to the 4th over 4 factorial. Ix to the... Yeah, I know what the problem is. I watched that stupid Red Sox game till after midnight. That stinking game. They're ahead 5-3 in the ninth, 2 outs, and what does he do? Double and then a home run. Kimbrel, and so I shut it off. All right, that's all right. Never mind.
What do you do to your summer classes?
What?
What do you do to your summer classes? I mean, the season just started.
I know, but I got this big bet on the number of wins the Red Sox are going to have. So now I'm a Red Sox fan, but now I'm kind of a fanatic because I need them to win 87 or more games. I know it. Oh, well. That's not a giant bet. Okay, only a couple years' salary. No, who cares? All right, no.
So will you not sign up for your class next semester in case you win?
What's
Will
that?
you still be here?
Oh, yeah. Yeah, it's not a big bet. It's just that I was so psyched this spring, like I always am over the Sox prospects, that I go overboard. All right, but anyhow, so here's what we got. E to the ix then is equal to 1 plus ix. You got it? I already wrote it. Now I've got I squared. What the heck is I squared? A negative 1. So it's a minus x squared over 2 factorial. Okay? Plus, I've got I cubed. That's a negative I. That's a minus I x cubed over 3 factorial. Plus, I to the 4th. That's 1. That's an x to the 4th over 4 factorial. Now it starts all over again. I to the 5th is the same as I. It's I, x to the 5th over 5 factorial. I squared is a negative 1. It's a negative 1 x to the 6th over 6 factorial. Okay, so here's what I've done. I've taken each of these x's and replaced them with ix. So I put ix here, ix here, ix here, ix, zip. Now, here's what I'm going to do. Let's see what we got. We've got e to the ix is equal to 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial plus ix to the 5th over 5 factorial. Boy, I'm hoping this is right here so far. X to the 6th over 6 factorial, etc. Okay. Whew, I hope so. Here's what I want to do. I'm going to separate this into 2 parts. Okay? The real part, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. Plus, how are we doing? I now have the imaginary parts left, and I'm going to factor out an I. Okay. I have an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Whoa! What do we have? We have Devin Lehman. Can't handle this.
You have an even and an odd set?
Well, we have an even set and an odd. Can someone tell me what one? Yes, Brendan. You bet. What is this? This is cosine x. Okay, that's what cosine is, all the even ones, plus I sine x. Those are all the odd ones. Believe it or not, this is a function. This is called cis function. It's used in certain applications. Okay, cosine plus I sine x. There's certain applications that use this. And here's the last thing we're going to do. And I'm out of room and I can't do it. Oh my gosh. All right, the last thing is this. I have e to the ix is equal to cosine x plus I sine x, the cis function. I'm going to let x equal pi. Now I can do is e to the I pi is equal to cosine pi plus I sine pi. E to the I pi is equal to, what's the cosine of pi? Negative 1. What's the sine of pi? 0. This is called Euler's formula. Sometimes given in this form. Sometimes it's given in this form. E to the I pi plus 1 is 0. Which it relates in one succinct little equation. E I, pi, 1, and 0 all together in one little equation. It is said to be the most beautiful mathematical equation of all time. This is it, right here. We just proved it. It's awesome. I think I may get emotional here, but all right, I'll try not to.
What is this kind of equation used in application? Like you said, I would be used in circuits and radio or whatever.
Yeah, well, sys functions are used in certain electronic applications. This equation is just beautiful in its own right. It's intrinsically beautiful. All right, so here's what you should be doing. That's it? That's everything?
That's the book?
That's the whole book? No, we got Calc 3 there. You should be doing homework, and Thursday I'm going to do a lab and review. Now, I get the impression that many of you, if not most of you, are behind in the homework. Given what I was saying in the beginning of class and getting the lack of response that I was getting. So get caught up, please, all right? Get yourselves caught up. Skip any baseball games, even if you're starting. You may have to tell the coach, Coach, I can't have to go to calculus homework. You have to do it. Get caught up, all right? Thursday, see you Thursday. I wonder how that would go over, Brendan.
One game I might start?
Yeah. I'll tell you, let me just tell you. I had a kid in my math team, East Middle High School, right? And he was my star. But he was also the star of the swim team. And the swim team had practice that day. We had a meet. We had 5 meets a year, math team, right? And I went down to the coach, and I said, Coach Bowles, I need this guy for this thing.
Who was it?
Coach Bowles was the coach.
The kid.
I'll tell you, Bird, Gary Bird.
Oh, just kidding.
Okay. Oh, you have to
I
take
thought it was someone else.
Oh, this is a way long time ago. But anyhow, so Gary Bird was my star, and he was a star on the swim team. And they had practice. I said, oh, you don't even have a meet. I need him for my meet. He said, no. I said, what do you mean, no? He said, we need him. A swim team, you have to do these practices, and you can't skip a practice. I said, what are you talking about? I need him for my meet. He can skip a practice. He said, no.
You can get academic passes from...
He said if he skipped that practice, Gary Bird was off the team, the swim team. That's what he said. And so I left it up to Gary, and Gary went to swim team practice and missed the math team. And I was so mad at that stinking
You didn't
coach.
just call your AD? Be like, hey, your swim coach is going off.
No, the head of the PE department was totally in back of the swim coach guy. He was totally supporting him. It was.
Did you lose the meet?
We didn't come in first. I don't know what we came in, but we did not win that meet. That's for sure. I don't know. It was pretty bad, Brendan. Yeah. What's that?
Were you a swimmer?
He was a swimmer. Yeah, the swimmer. And the swim team coach said, no, he can't miss practice for my math team. Oh, I was so mad. I lost that, though. I lost that
Oh, by the
argument.
way, you should totally tell Professor Topier he needs to look at himself. Because I want to, and it's not going to get anywhere. But he was like making the entire class feel like we were idiots this morning because we didn't know Calc 3 when the co-requisite for the whole class is Calc 2. Like, he knows walking into it, there's one person in that class. Like, he asked the first day, is anyone in Calc 3? One kid raised their hand. And then today he was like, so what's this going to be? And crickets. And it was like,
Listen, all you can do when he does that is think to yourself, obviously he's overcompensating for some lack in his own personal life by making him look big and you guys look small. And that's what you have to think to yourself and just chuckle to yourself. That is so pathetic that he has to make fun of you guys and he has no right to do it.
it's like it's the same shit every time. I got a really big kick out of it. Like, I think it was last week. We was like talking about the end of the semester, and then he just goes, so I know we have like 2 chapters left, but